Okay, and sharing. Okay, you can see my screen.
Yeah.
Yes.
Okay, good. Again, I ask you to open the cameras, everybody. Again, with the usual business, if there isn't any alert or alarm, we will leave the Zoom open. We go to the shelters or safe rooms and come back after 10 minutes or 15 minutes, and then we will add that time at the end of the lecture. Another thing is that, as I said, I want to add a few lectures. I mean, first, as I already told you, I will be away. I'm supposed to be, if everything goes well, I'm supposed to be away for a travel in May. So we need to compensate for that. Plus, I don't think we will be able to cover everything in a shorter semester. So we definitely have to add a few lectures. So one sort of obvious time to add a lecture is next Sunday, 1 week from now, the same time, the usual time of the lecture. Is there any problem for any of you with that? Okay, if there isn't, please write me. Otherwise, I'll just send out a notification for everybody about it. Okay. Um, so let's start with a recap on what we did. Uh, so we started to discuss special relativity, SR for short. What we did was first we looked at the Michelson and Morley experiment, right? And the Michelson-Morley experiment talked about two observers. One, call it O, and the second one, call it O prime, that is moving with respect to O. And we said that there is a source of light and that emits a light. So event number one, at t equal t prime equal to 0, x equal x prime, y equal y prime equal to 0, z equal z prime equal to 0. Crest of light emitted. And then at time t, x, y, z, crest of light was the point here. For the second observer, we'll also agree that according to her measurements, it's t prime, x prime, y prime, z prime. And both observers agree that x squared plus y squared plus z squared is equal c squared t squared. And the same is true for O prime. Although in general we said that x is different than x prime, according to this picture, y is equal to y prime, z is equal to z prime. That means that t must be different than t prime. So the time and space are related via what is known as the Minkowski space. Here's a 4D space-time. Both, though, agree on a quantity which is known as an interval. Which is defined as interval squared and denoted normally by delta S squared. There is a delta because this is a difference between two separate events and is defined as minus c squared delta t squared plus delta x squared plus delta y squared plus delta z squared. And both of them agree, and we saw the analogy of that is a distance in 2D Euclidean space. Analogy, distance in Euclidean space. Then we started to use some new notation. We define four vector of coordinates by x mu with an upper index. Mu goes from 0 to 4. X0 is ct, x1 is x, x2 is y, x3 is z. And then I also introduced a matrix, which is a very simple matrix, but I use two lower indices for that matrix. Eta mu nu, which is a minus 1, 0, 0, 0, 0, 0, 0, plus 1, plus 1, and plus 1. So it's all zeros except from the diagonal. And the diagonal is a minus 1 at the bottom top left, and then everything else is a plus 1. I did mention to you that in quantum field theory or anything associated related to particle physics, they also make use of the same matrix, only with an opposite sign. Q of t is minus eta gr. Let's call it like that. Astronomy and relativity, the standard notation that you find in all textbooks is this. So we're following it. And using this new notation, we could write down the interval delta s squared as a sum from mu and nu from 0 to 3 of eta mu nu delta x mu delta x nu. And to make your life more confusing, we're going to use the Einstein summation convention, which states that if we're seeing an equation that in one side of the equation we're seeing the same index that appears twice, once as a lower index and once as an upper index, then we understand that we sum over this index. It is known as a dummy index. So we don't need to write the summation. So we simply write eta mu nu, delta x mu, delta x nu. And I stress it again, when you're writing down an equation, if you should see index can appear twice, only once as an upper and once as a lower. If you see the same index that appears twice as an upper or as a lower, that means that you're doing something very wrong. You should check yourself. This cannot be. And if it appears once as a lower and once as an upper, that means it is summed over. And then that's why we call it a dummy index. Okay? That is known as the Einstein summation convention. If you get confused, which you may, simply add up the summation. So it will clear what you're doing. Then we defined Lorentz transformation. This is a transformation from one coordinate system to another. So from the blue to the red or from the red to the blue. A transformation between one coordinate system to another that conserves the interval. That is a definition of a Lorentz transformation. And then we show, and then we say how to describe that. And so we describe it. So one Lorentz transformation is translation. That means shift of the origin. Mu is some constant. The other one is multiplying the 4 vector x mu by some 4 by 4 matrix. So x mu prime is lambda. And note how I write it, because that is very important. And you'll understand today why this is very important. So obviously one upper index and one lower index. And they're not one on top of the other, but in diagonal. Mu prime, there is a space, and then nu x nu. That's how I will define the Lorentz transformation. And we show that the requirement for um, conserving the interval is translated into the mathematical requirement eta rho sigma is lambda mu prime rho lambda mu prime sigma eta mu prime u prime. And then I argue that every matrix that fulfills this equation is a Lorentz transformation. And I gave two examples. So one is rotations. Lambda mu prime nu 1, 0, 0, 0, 0, 0, 0, cosine theta, sine theta, 0 minus sine theta, cosine theta, 0, 0, 0, 1. This is a legitimate Lorentz transformation. Just to make sure that you're all with me. In here, how many equations are there?
16.
16.
Yeah, that's right. And in each of these equations, how many terms you have to sum?
16.
16. So there are a total of 256 terms. Okay, most of these are zero because the matrix eta is mainly zeros. Right? But overall, this is a very compact form to represent actually quite lengthy set of operation. All right. So rotations are legitimate Lorentz transformation, and the third is boosts, which can be thought of as a rotation where time is one of the components. Lambda mu prime nu is cosine hyperbolicus of phi minus sine hyperbolicus of phi 0, 0 minus sine hyperbolicus of phi cosine hyperbolicus of phi 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. Of course, this is in the time boost in the time in x. This is rotation in the x and y. Of course, theta is between 0 and 2 pi. But phi can go from minus infinity to plus infinity because of the nature of hyperbolicus functions. And I showed you that although this is a very abstract, it is in fact coincides with what you know of, right? If I just write down x mu prime is equal lambda mu prime nu x nu. So pt prime x prime y prime z prime is equal cosine hyperbolicus phi minus sine hyperbolicus phi 0, 0 minus sine hyperbolicus phi cosine hyperbolicus phi 0, 0, 0, 0, 0, 0, 1, 0, 0, 1 dt x y z. We show that so ct prime is equal cosine hyperbolicus of phi ct minus x sine hyperbolicus of phi, and x prime is minus ct sine hyperbolicus of phi plus x cosine hyperbolicus of phi. And then at beta x prime equal to 0, the velocity beta is v over c, is x over ct, is tangents hyperbolicus of phi. And then we got from cosine hyperbolicus of phi 1 minus tangents squared hyperbolicus of phi minus 1 minus 1 half. So this is 1 minus beta squared minus 1 half, which we call gamma. Then sine hyperbolicus of phi is gamma squared minus 1 half, which is gamma beta. And so from here we get that ct prime is equal gamma ct minus beta x, and x prime is equal to gamma x minus beta ct, which is the familiar looking Lorentz transformation that you know from first year studies. So what I did is not telling you anything new. Well, it is, right? But it fully coincides with the thing you already know first year. And then the last thing we did on Thursday was to look at the time dilation. And I spoke about what happens if I'm holding a clock with me. I have a clock here. And the clock, of course, relative to me is not moving. So if the clock is not moving, then the two ticks are called the proper time. So delta x, if delta x, delta y, delta z is equal to 0, delta t is dt, it's called the proper time, also known as t tau. Then we have delta tau squared is just minus delta s squared over c squared, minus 1 over c squared eta mu nu delta x mu delta x nu. So that's for me. If you are seeing me moving, right? So the second observer is the clock moving. Delta x prime is v delta t prime. And for you, delta tau prime is delta t prime squared minus delta x prime squared over c squared 1/2, which is because delta tau and delta tau prime has to be the same. Maybe I should write down delta t prime 1 minus beta squared 1/2, but delta tau must be equal to delta tau prime because of this definition here. And so you get the delta t prime is 1 minus beta squared minus 1/2 delta t, which is gamma delta t. So you will be seeing my clock ticking slower. Right? I would live longer. Of course, I couldn't really live longer. If my biological clock says I'm going to die at 100, I'm going to die at 100 years. But from your perspective, it could take much longer if you see me moving all the time. All right, now before we move on, do you have any questions about anything we said on Thursday?
Yeah, I have a question. So when it comes to boosting and rotation, how do we determine what axis we're doing it by?
You choose. I mean, boost and rotation, you choose. I mean, you select which ones. It depends on the problem at hand.
Okay. But
There's no
okay.
general. Here I said, okay, I want to do a boost in the X direction. You could do a boost in the Y direction as well, right?
Mm-hmm.
I choose to do a boost to some velocity, right, which is determined by beta. But you can do a boost to another velocity, which is beta 2.
Okay.
So it's determined by the problem at hand.
Okay.
All right.
Is there an intuitive way to understand why boost is a rotation in the TX plane, for example?
it's just, I don't think intuitive, it's just a name, right? I mean, mathematically, when you speak about what I said, right, look at the logical mathematical structure. We said that what we need to do in order to make any Lorentz transformation is to take the 4 vector and multiply it by a 4 by 4 matrix that space-time independent, etc. So you can think of what types of 4 by 4 matrices you can have, right? So the ones that do not involve the time, these are the rotation matrices. The ones that do involve the time, again, the mathematical structure is very similar. I mean, I guess that's all I want to show here, that the mathematical structure is exactly the same as rotations. It's just a name. It's a rotation. A rotation where time is involved is called a boost. I don't think there is much more than that, to my understanding.
Okay.
All right. Okay. So now we're going to start to get slightly deeper into the math. I need to do, this is, I told you, it's a combination of math and physics. And what I'm really going to do is, I'm going to give you some math that is necessary to understand the rest. Then we'll do the physics and we see what it's good for, this math. Then we got to do some more math and we're going to do some more physics. We'll see how it goes. So now we're going to speak about math. This is going to spend most of the next hour. And the math is called vectors and tensors. It's not this one, it's this one. Vectors and tensors. Actually going to talk a lot about them. So this is the starting point of vectors and tensors. Let's say 1. Okay, we do want, of course, the constant that what we really need and want is to discuss physics in this 4-dimensional Minkowski space. So we need to define the formalism of working with vectors and tensors. We're going to do it gradually. Otherwise, you might easily get lost, and I don't want to have that. And again, I remind you, if you don't understand something, stop me. It's not that difficult, but it can be very tricky. If you haven't seen that before, it can be very tricky and it can be very confusing. We're going to do one by one, step by step, and if you feel that you're losing me, then just stop me on the way. Okay, I don't mind adding up another lecture. I do mind that you don't understand. So we start by 4 vectors. What is a vector? It is not the first time you're seeing a vector, right? You've encountered vectors. What is a vector?
Simply put, something with magnitude and direction.
What? Magnitude and direction. Yeah, well, yeah, okay, that's what you were told. So
Vector is an element in a vector space.
yeah, that is true. Vector in the vector space.
It can virtually be anything you want.
No, it cannot be anything I want. That's not true. We had certain rules. It does fulfill certain conditions, such as being an element in vector space. Magnitude and direction, that's a little bit problematic. You're going to see shortly why this is problematic. In essence, it is true, but it's not. It's really not exact. Okay, so I'm going to have a new definition of a vector for you guys.
It's the magnitude and the direction it is a certain point of space. Like it's
Sort of. You got the right thing, that the vector is that's a very good point, actually, that the vector belongs to a certain point in space. But let's get to that shortly. So basically, I've introduced the vector, right? 4 vector of location, right? So there is a space-time coordinate right? Which I wrote CT, X, Y, Z, and I wrote them as X mu, right? Now we saw that when we look at this location and when we're making a Lorentz transformation, right, these coordinates change, right? Under Lorentz transformation, LT is Lorentz transformation, right? The coordinate for vector, let's call the coordinate for vector, X mu transform according to X mu prime is lambda mu prime nu X nu, right? That's what we discussed on Thursday. So now I'm going to define a vector in general, not the coordinates, any vector. Definition. A 4 vector is any quantity whose components undergo the transformation V alpha goes to V alpha prime, which is lambda alpha prime beta V beta, when the coordinate system is transformed in the same way. That's my definition of a vector. Okay, so it is defined by the way its components transform under Lorentz transformation. Now it can be any quantity, of course. Velocity, acceleration. We're going to encounter several 4 vectors. In fact, the correct technical name is called contravariant 4 vector, for a name which will get clear in about half an hour. This is called a contravariant. All right. So I use a Lorentz transformation to define that. Of course, every 4 vector, how many components does it have?
4.
Oh,
Four.
What? 4, right? Obviously, it has 4 components. It has now. When I say vector, that's another thing. I always mean contravariant vectors. It's going to be in other types of vectors, which you're going to see shortly. When I say vector, I always mean contravariant vector. Okay, so contravariant 4 vector. This is the correct name, but the short is simply vector. Okay, vector for short. So when I say vector, it's always contravariant 4 vector, no exceptions. And then so now, so it has 4 components, obviously. It has 4 components. And then one of you said something which is very true. The other very important concept is that a vector belongs to a point in space-time. Each vector is located at a given single point in space-time. This is crucial. I mean, in Euclidean spaces, right, we normally denote vectors with arrows, right? So you can think of, or mistakenly think that vectors connect one point to the other, right? A and B. Then you can slide them back and forth. And that's why we also, we know the notation of vectors is always with an arrow, right? So no, that's a mistake. And that's a mistake because that is not a mistake, of course, when we speak about Euclidean spaces which are flat. But when we go to spaces which are not flat, but curved, which we're going to do shortly, then you cannot do that anymore. So think about the surface of the Earth. I mean, every time you're confused, just take a ball. Right? Consider the surface of the Earth, right? Think of the way like you're traveling from here to the US, right? In an airplane or a boat, whichever your favorite way. You cannot go through, the shortest path would just take you straight, but then you have to go through the center of the Earth, which you cannot. So you're obliged to be on the surface of the Earth. Okay.
So the main difference between this definition and the traditional one is generally the space it occupies.
No. Yeah, this is the correct definition. Okay. Well, wait with this question, you will see that. Okay. So this is the definition of a vector, right? This is what's written here. This is the definition. And this is a very important property of a vector. Each vector
Can you explain why it is contravariant? I mean, like contra against the variant.
what?
Can you explain why it is called contravariant vector?
You will get that before we're going home today. You will understand why it's called a contravariant.
Okay.
Okay.
Yeah, it's confusing.
Okay. What am I doing? Again, this is needed because we're not going to deal in general with flat spaces. This, I mean, that is related to a point, which means, by the way, that the concept of direction is not really specific. We cannot really define a direction in spaces which are not flat. So right, so the correct way to think of it is the following. So let's consider space. It's going to be a 2D space, which is curved. So again, think of surface of the Earth. Right? Of course, it's going to degeneralize to n dimensions, etc. I have not defined it yet. I will define it later. We call this a manifold. So just for you to know, when we say a manifold, we mean a space which is locally resembling Euclidean, but globally it is not. Okay, let it think for a second. So for example, the surface of the Earth, if I'm looking locally in my room or in the classroom, I can mistakenly think of it as being flat. But of course, globally, the surface of the Earth is not Euclidean, it's a sphere. Again, some people still don't understand that, but that's not my fault, right? Locally, I can think of the surface of the Earth, I can resemble it as a Euclidean flat space. Of course, the closer I get to a point, then the better it is, better approximation it is. Although globally it is not. Okay, this is the manifold, without explaining what is a manifold, but to get you this is the right intuition of what is a manifold. The easiest way to think of it is in that sense. So it's a smooth, it doesn't contain any spikes, it's not a porcupine, just right. It's called a manifold. I'm not sure I'll get to the full definition because it's a little bit of math and we don't really have the time to get deeper into that. Then I choose a point P on that manifold. And then I look at all the set of all possible vectors which are located at this point. And this set of vectors form a space. And this is called the tangent space. TP. Tangent space to P. So the set of all vectors attached to the point P comprise a plane tangent to that point. So really, again, think of a sphere. We take a ball and then take a wood or a piece of flat paper, just attach it. It will touch the ball at a certain point, the point P, right? So if I have a ball here and I have a flat space, I don't have it with me, but it will touch the ball at one point. That is the tangent space to P. TP to the point P. All right? And so all the set of all the vectors, they form this the tangent space. Now, one thing is that the thing to remember, right? We're drawing vectors as arrows. We do, but they actually touch the surface only at the point P, not at other points. Okay, which you can easily visualize by just taking a flat surface and attaching it to a ball. They touch but on only one point. So we'll keep on describing vectors with arrows. That's fine. But remember that they only belong to that point P, and that also gives us a quite substantial confusion about what is the direction of a vector. But we'll talk about that in time. Right now, we don't need that. So TP is basically the abstract vector space. TP is the abstract vector space. And then whatever you said, again, I don't remember which one of you said, is correct. I mean, it fulfills all the properties that you know from vector space, right? From linear algebra, right? There's a vector space, and it has all the properties from that you have. This is a collection of vectors, a collection of vectors of objects. Well, these are the vectors, of course, that can be added, multiplied by scalars, in a linear way. So, if you have any two vectors, V and W are vectors A and B real numbers, then obviously A plus B, V plus W, that's a new vector, which is AV plus BV plus AW plus BW. That's kind of clear. Of course, every vector has an origin, namely there is a zero vector. There is a zero vector such that V plus 0 is equal to 0 for any vector. Now, we can take, there are some other structures which we don't need, right? Inner product, etc. So we don't need them. So far, so good? Yeah?
Yep.
Okay.
So the manifold isn't a vector space?
No, the manifold is not a vector space. We're talking about a tangent space to a point P on the manifold. Okay. The manifold is, I told you, is some sort of geometrical space, which is locally Euclidean, but globally it is not. And the correct thing, the simplest thing to think of it is the surface of a sphere, 2D. There are other examples, of course, but right now we're not there yet. We're talking about special relativity, so we don't do curved spaces. I just want to highlight the fact that vectors belong to a single point, not as you may mistakenly think that they connect to different points. They're not. Okay? What we care about, so this actually this is the only thing I wanted to have here. I don't want to confuse you more than that. Just to ensure that you all understand that vectors belong to a single point in space-time. Okay? Good. Now I want to speak about basis for vectors and the components. So what is a basis? Oh, obviously, we have vectors, and it's often useful, we don't have to, of course, but it's often useful to decompose the vector into its components at a given basis, right? What is a basis?
Take some usually orthogonal vectors that span the space, and you express any vectors as some of those.
Right. So the first thing is a basis is a set of vectors that what?
That isn't linearly dependent on each other.
Correct. So the first thing is that it's linearly independent. Means that there is no vector in this basis that is a linear combination of other basis vectors. And it spans the vector space. Right? Meaning every vector can be written as a linear combination of the basis vectors, right? So any such set of vectors is a basis. Given a vector space, how many different bases are there?
Infinite.
Infinite, right? So for each vector space, we can think of infinite number of different bases. For each vector space, there are infinite number of bases, legitimate bases. But what can we tell about all the different bases? Well,
What do you
they
mean?
all have
they can describe the vector space
Yeah.
fully?
Well, they all span the vector space, right? What do you mean by describe? Well, what I mean is something different. How many vectors are there in each of the bases?
At least D, if D is the dimension of the.
At least, exactly. You cannot have more than D because then they become linearly dependent. Right?
Right, right.
So you have exactly. So all of them have the same number of vectors. All bases have the same number of vectors known as the dimension of the space. Of course, in Minkowski's space, the dimension is 4. You need 4 vectors to span the Minkowski vector space. Now, there is one subtle point which needs to be highlighted, right? And that is, when we speak about the vector doesn't care about the basis, right? We can select different bases to describe the same vector, but the vector doesn't change when we're changing the basis, right? Its components change, right? The same way as we had this distance, right? When we're changing the x and y basis, right? We change the components of a vector, the way we describe the vector. Well, we don't change the vector. Okay, you're all with me? Again, I'll write it down. Just make sure that you're with me. A vector is defined by itself, regardless of its decomposition into components with respect to any arbitrary basis we may choose. Simply, the basis vectors are helping us, right? So let's say we have a vector. We have a vector here, right? Call it V. Let's say it's Vx in the x direction plus Vy in the y direction, right? This will be the components of the vector, right? But in a different basis, x prime, y prime, it's the same vector V. It's not changed. Now it will be Vx prime, x prime plus Vy prime, y prime, right? We didn't touch it. The vector doesn't care about the basis. In different bases, vectors will be described with different components, but the vector itself not. That's the point I'm trying to highlight here. Yeah?
Yep.
Okay. So again, let's look now at this point P and we look at the tangent space. So consider again the tangent space P, TP at point P. Set the basis of TP of 4 vectors, which I called E mu. Mu is CT, X, Y, Z, or 0, 1, 2, 3. Right now, for simplicity, we just take these basis vectors to be aligned with the coordinates. Which I don't even need to write it. E.g., the basis vectors are assumed to be aligned with the coordinates. Right, so E1 is aligned with X1, etc. Now, just to be sure that you're with me, I wrote it, first I wrote a lower index and I put it in parentheses because I'm talking now not about the components of a single vector, but of a set of 4 vectors. And that's why I put the parentheses. So E mu, these are 4 different basis vectors.
So if I want like the first basis vector, I do E in parentheses 1 or something like that.
Yeah, this really represents the vector in the x direction, right? Like,
Okay.
I don't know, like this one here, right? This will be E1. And this will be E2. All right? If I have a vector, call it A, let's call this A rather than V, then I can write down each vector. A is A mu, E mu. A mu is the component, right? Again, look at the picture that I just drew, right? A is the component, and E represents the basis vector. Of course, there is a summation here over mu. From 0 to 3, A mu, E mu. A mu, these are components of A in the basis E mu. Of course, I wrote the basis vectors with a lower index, so I can use the Einstein summation convention. All right. If I'm using a different basis, like in this small picture I drew, right, the blue one, then A mu will get different components. A will get different components, but of course the vector itself, A, nothing happens to it. Now, in fact, the classical example of a vector here, I'm taking you slightly on. You know what? Let's draw it in. So, classical example is what's known as a tangent vector to a curve. It's something which will repeat itself. So let's say we have some sort of a manifold, M, right? And then I have a point P on the manifold. And what can I do? I cannot do too much on a manifold. I can do this, define some curve or path. So think of it like that, right? I am going on a holiday, I'm going on a vacation, and I like to hike, so I'm doing some hiking, and I tell you my path, right? This is what I can do. This is my path of my holiday. And the only way I can describe this path is by some parameter lambda. So here is lambda equal to 0, lambda equal to 1, lambda equal to 2. Lambda describes where I am on that path. Okay? So now I'm going through P. And And I can define the vector that is tangent to that curve at the point P. So the curve itself, right? The curve is specified by x mu lambda, right? How the coordinates change as I'm going along the curve, along the path lambda. So the components of the tangent vector, the tangent vector, has components. What will they be? Tangent vector is v lambda. There's nothing really that I can do except the only basic things, right? dx mu over d lambda.
Mm-hmm.
There's nothing else that can be done. And the vector v is just v mu e mu. Now, when we're making a Lorentz transformation, of course, the coordinates x mu change, but the parameter lambda doesn't change. Right? Under Lorentz transformation, right? Look at that, right? X mu changes, right? Lambda does not change. So v mu changes like x mu, which proves that this is indeed a vector.
What is v mu?
This is the tangent vector to the curve. So what I'm doing, I have some manifold, right? Again, think of it, I am traveling on Earth, right? I take a boat and I sail, right? So my boat describes a path on the curve, right? And the path is specified by some parameter lambda. For example, you can think of it like time, right? I'm sailing to America, then I can, tell you, like I have a radio connection and internet, and I can tell you where I am. Or you can specify that, by my plan, right? So at day one, I'm supposed to be in this location. Day two, I'm supposed to be at that location. So if I tell you what is lambda, you're supposed to know where I am on that path.
Right.
Right? So you can define a tangent vector to the curve. So you can take a point P, you know where the
So
curve is
if I
heading.
have a given path.
Mm-hmm.
So for a given path, v, the vector that is tangent for to the manifold,
Is tangent to the manifold at the point P.
at the point P.
I insist, at the given point P, yes.
And P changes with lambda.
Yes, that's true.
So V changes with lambda. Okay.
But V is defined at P. Okay, and I can define the tangent vector to the curve at the point P by specifying the components like that, right? dx mu over d lambda.
Okay.
And what I did here, I just proved to you that when I'm making some transformation, the components on V will transform exactly the same way as the components of X, which proves that this is indeed fulfilling the requirement from a vector, as I defined above. Right? When X changes, V changes in exactly the same way. So this is a vector. Again, it's a little bit abstract, but at the end of the day, conceptually, mathematically, it's very simple, right? I said any quantity that transforms under Lorentz transformation the same way as the coordinate system, I call it a vector. In fact, I said covariant vector. But now I want to do something else, right? So this is the components of the vector, and this is the set of basis vectors, right? It's not the same thing because this represents one vector. This is a set of 4 basis vectors. Now I'm asking, how is this set transforms under Lorentz transformation? How is this set of basis vectors transform under Lorentz transformation?
What do you mean, how does the set transform?
Okay, let's do that. I'm going to argue that the transformation law of this set cannot be the same as the transformation law of the vectors. So let's do that now. Transformation law of basis vectors. We said that V is V mu E mu. Sum from mu 0 to 3. Now I want to change basis. So I'm transforming the coordinate system. So transforming the coordinate system, so now E mu would go into new coordinates, say E mu prime. Now I said the vector itself doesn't care about the coordinate system. It's there, right? The vector itself doesn't care which coordinate I'm trying to describe it. The vector will still be there. So I can write down V as V mu E mu. So in the new coordinate system, it will be V nu prime E nu prime. Now I know how to relate the components of the vector in the new coordinate system to the old one, right? This is lambda nu prime mu V mu, right? E nu prime. Right? Because I define the transformation law of the components of a vector, which is exactly that. Now, this is true for any components, any vector. I did not specify which one. Which means that I can write down E mu. This is the old basis, is lambda nu prime mu E nu prime. So we get the new basis. So we get, so this is the old basis, right? Without the prime, written in terms of the new basis. But of course, we want to write the new basis in terms of the old basis, right? So to get the old basis, we take the new basis and we multiply it by Lorentz transformation, right? Lambda is a Lorentz transformation. So what do we need to do to get the new basis in terms of the old basis?
Multiply by the opposite, the
Exactly. By the inverse Lorentz transformation. You're right. But what is an inverse Lorentz transformation? It's also a Lorentz transformation, right? If I'm Lorentz transforming from frame O to frame O prime, right? The inverse is also a Lorentz transformation, but now from O prime to O. Right? So that's why we're going to have a quite subtle notation. So we need to multiply by, so to get the new basis in terms of the old basis, we multiply by the inverse Lorentz transformation, lambda minus 1, nu prime mu. Now comes the subtle notation. Remember, I told you to keep a space here, right? Since the inverse Lorentz transformation is Lorentz transformation, I'm going to write it as lambda, but now the first index is going to be a lower and the second index is going to be an upper. So we can write E nu prime is a lambda nu prime mu E mu. Of course, this is equivalent of writing lambda nu prime mu lambda sigma prime. Mu is a delta sigma prime nu prime. Okay, there is an alert here that we may need to go to shelter since it's not necessarily. Does any of you need to go to a shelter right now?
I might need to.
I might need to too. I got an alarm alert here right now. So right now what I'm going to do, I'm going to keep on. If none of you need to go, I'm going to keep on. And if there is an alarm, of course, then I'll go. Because I am fortunately close enough so I can go there within 1 minute. But right now, unless you need to go, then we'll just keep on until there is an alert. So, of course, this is written as lambda nu prime mu, lambda sigma prime mu is just a delta, or lambda nu prime mu, lambda nu prime rho is delta mu rho.
So,
Just a second.
I guess
By the way, just a second. Delta is the only symbol right now. It's really a tensor, but I haven't specified it, that I allowed to write with two indices, one on top of the other. Is the only one. This is the only exception. Yes, please, question.
Why do we care about the spaces?
It will get clearer and clearer. It's crucially important. Well, right now, actually, you can see that, right? If I'm writing down lambda nu prime mu is not the same as lambda nu prime mu, right? It's the inverse of each other.
Yes. But we can write them on top, and it's still them like watching them. So why we need the spaces?
You will see. Okay, you will see. It's part of a much bigger structure. Okay. We will get there. You'll see it's crucial. For now, just wait, and we'll get it. But here, this already explains the term that I was asked. Why do we call it a contravariant vectors? Right? And now the answer is clear, because the transformation law of the components of a contravariant vector is the opposite, namely contra to the transformation law of the basis vectors. This explains the name contravariant. Okay, I promise you we'll have an answer to that. So now we have an answer. Don't worry, everything I promise I'm going to feel. There will be no promise that I give you that will not be answered.
What is exactly opposite here?
The transformation. We're using the opposite transformation law, right? The opposite Lorentz transformation. Right? To get from if we want to switch the coordinates from O to O prime, right? We define the vector such that its components also transform the same way as the coordinates, but this is the opposite to the transformation law of the set of basis vectors.
Thank you.
Okay.
So basically, when transforming, we're basically managing the superscript and subscripts, kind of.
Not yet. Wait with that.
Okay.
Transforming is transforming. Now I want to keep on generalizing, and I'm going to talk about covariant vectors. And the dual space. Now, I'm pretty sure you have heard of dual spaces in linear algebra. Have you? Yes, but some of you may not fully grasp the...
No, I didn't.
Sorry?
I didn't hear about them, so could you explain what they are like?
מה המונח בעברית? מה
Dual
המונח
space.
בעברית?
מרחב דואלי, dual space. מרחבים דואליים. Did you study quantum mechanics?
Yes.
Yeah.
Cars and cats?
Yes.
Yeah.
Did you study linear algebra? Row vectors and column vectors? Yes, Azaka? Okay. So we're going we stop here. We'll be back in 10 minutes. See you in 10 minutes. The Zoom is open. יתמוך בך. לא, עכשיו בהפסקה, כי לחלק מהסטודנטים יש הזקה. אתה יכול ללמד חלק מהסטודנטים חלק מהסטודנטים חלקה. לא, ברגע של החלק מהסטודנטים שיעור של מס. כבר לא הייתה הסקה, אנחנו לא צריכים ללכת לזה. אני באמצע שיעור עכשיו. אני כרגע באמצע שיעור, אז לעשות איזשהו.
הוא בדיוק שלך כשהוא עצוב.
Okay. Can we resume back? I assume everybody's okay. Give another minute and then we can resume back.
Can I ask a little question?
Yeah.
Can you explain again the covariant, the contravariant indexes, because I didn't really understand it, and why is it called this way?
Well, the origin of the name, it's contra to the way that the basis vectors are being transformed. But if it goes with the basis vectors, then it's called a co, and you'll see it with a lower index. So a co-vector is going with a lower index, and a contra vector goes with an upper index, because it goes the opposite way to the way that the transformation law of the basis vectors are.
So if we have some transformation and one of the indexes is changing with this transformation, it's a covariant of the index. And if it goes with the opposite transformation, it's a contravariant index.
Yeah. Contravariant indexes are upper and covariant are lower.
Mhm.
Okay. So let's move on. So the essential thing is that the transformation laws of the components of the contravariant vector is the opposite to the transformation law of the set of basis vectors. And that's why we label them with upper index versus lower index. Okay? Yeah. Did I lose people? No, I think everybody's here. And because this notation of upper and lower indices, right, ensures that when we're summing, then we're left with something which is unchanged, which is the vector itself. But we can generalize that. So the idea is, maybe I should write it down, right? Transformation law of the components of contravariant vectors is opposite to that of the set of basis vectors. Now, one can think of other objects. The transformation law are the same, not the opposite, to that of the transformation law of the basis vectors. Of other objects whose transformation law is the same as those of the set of basis vectors. So once we have a vector space, right, we can always set another vector space which have the same dimension, which is known as the dual space. So once we have a vector space, TP, right, we can set another vector space is known as the dual space. Which is denoted by TP Or another name is the cotangent space. Cotangent, which is known as TP star. This is the dual vector space. I'm pretty sure you should have at least seen that in the linear algebra course.
Yeah.
Yeah, you have. Other people here?
Yes.
You admit. This is noted by TP. They have the same dimension. And the dual vector space, what are the objects in the dual vector space? Who lives in this space?
Covectors. Things that turn vectors into integers, to numbers.
Into numbers, exactly. So the dual vector space consists of what we call dual vector. I'm going to use a more precise definition. It's really a linear map. So the dual vector space consists of linear maps from TP to real number. So if omega belongs to TP star, is a dual vector, then it's really a mapping. It's a linear map. Then it is a linear map. Namely that omega that operates on AV plus BW, right? V and W belongs to TP is A omega operating on V plus B omega operating on W, which is a real number. That's what it means. Of course, in quantum mechanics, you think of bras and cats. It's not a real number, it's a complex number. But it doesn't matter. The idea is exactly the same idea. So objects of the dual space or the cotangent space, they live in a different space than the tangent space vectors, right? But they can act on them, producing real numbers. Right.
Can you repeat that? Like you said that they like the bras and the cats. Like how they like them.
Well, in the same sense, right? You can think of a bra and a cat, right? Phi, psi, this is a real number. This is a complex number, right?
Mm-hmm.
And psi, right, is part of a vector space. So you can add them, right? You can treat it as psi1, A psi1 plus B psi2. And the same you can do for the bras.
Okay.
Right?
Okay. I now. Okay.
A prime phi1 plus B prime phi2. Right?
Yes. Then
The way I think of them, right? These are different objects. They live in different spaces. They can talk to each other. Okay. We'll get to that in a second. Let me, because we need to get to somewhere before we closing this. So I'll come back to them. I'm not going to forget you. So this is actually I just jumped, but that's exactly what I want to say now. That these maps by themselves they form a vector space. So if omega and eta are dual vectors, these are also called dual vectors. Covectors, dual vectors are all the same words. Dual vectors. Then A omega plus B eta that operate on V. Right, this is the way I write it. A omega, because these are linear maps really. It's just A omega operating on V plus B eta operating on V. Now, since they are forming, the part of the dual space, we can introduce bases for the dual space, right? So we introduce basis for the dual space. And of course, now it will be theta with an upper index. And the requirement from these vectors, covectors, right, to form a basis is the way how they act on the basis of the real space, such that theta nu that operates on a E mu gives a what? What real number is it going to give?
1.
Being a 1 or
0.
0. So really, it's a delta function, delta nu mu. So similar to any normal vector, we can always write omega as omega mu theta mu. Now omega, which is an element, omega is an element of TP star, dual space, is a covariant vector. Another name for shorten is simply a covector. So when I say covectors or covariant vectors, I mean the same objects that are not vectors, but are covectors, right? These are maps. Another name, which I don't see how we're going to have time, definitely not in a short semester, it's called the one forms. There's a whole theory of what's called P forms. Some of it you know, nobody told you about that, but you already know. We won't really have time, unfortunately, to talk about it. That's another name. It's all three names of the same thing.
I'm a little confused.
What do you
So this dual space is a relatively new concept for me, and it's very abstract. Is there any physical examples?
Yeah, I'm going to
That-
give you. So give me a few minutes before the end of this lecture. I'm going to give you an example before we go home. But
Okay.
let me finish. Because we have these components, then there is a very simple way of writing the action of a dual vector on a vector. So using components, using component notation. This actually may already help you see things. So if omega is operating on V, right? Now I can write omega as omega mu theta, right? So I have omega mu, V nu, theta mu that operates on E nu, right? Omega mu and V nu are components, so these are just numbers. I don't care about them, right? Theta mu is the vector, basis vector that operates on E mu, which is the basis vector of TP. So this is omega mu V nu delta mu nu. So this is just omega mu V mu. That belongs to R. That's the reason why we don't really need to use the basis vectors, theta and E. That also means that the opposite is also true. This is something which is slightly different than what you're used to from linear algebra. Namely, we can think of vectors as linear maps on the dual vectors. We can also, because of that, right? Because we can use that, and these are components. So we can also think of vectors as linear maps on dual vectors by defining V that operates on omega is just omega that operates on V, which is omega mu V mu. So essentially what it says is that the dual space to the dual space is the original space. And the transformation law of the components of a covector, right? Well, we already know that because this is exactly as the set of basis vectors. So transformation law of components of omega mu. Omega mu prime is lambda mu prime nu omega nu, and of the basis and their basis vectors theta mu prime is lambda mu prime sigma theta sigma. So there's nothing really we can do, but note that this is exactly the opposite transformation law to that of the components of a vector. And that means that the scalar function that we get here, right, this is R, right, this is the scalar function, is indeed invariant under Lorentz transformation. It is a scalar, right? We're changing the under Lorentz transformation, right? Omega mu V mu is equal to omega mu prime V mu prime, which is admitted is a scalar. Okay, now you ask for examples. Let's give a few examples. So the simplest way and the most familiar way to think of things, you think of vectors as column vectors in n-dimensional space. So V, I'm just going to write it as V1, V2, Vn. And covectors would be row vectors. And what is the action of a dual vector on a vector?
Number. What is that number equal to?
The sum over vi omega I.
Right. Which is exactly what is written here. I told you there's something bigger here. Right, this and this is the same thing. The second example, which we already discussed, is quantum mechanics and vectors or Hilbert space, vectors in Hilbert state in QM. Vectors in Hilbert space are represented by cats, psi, dual space by bras, phi, and the action gives a number, right? Phi psi is a number, is a complex number. It's not a real number, it's a complex number, but the idea is the same idea, so there's nothing alarming. The third example is a gradient, right? This is a scalar function phi. Gradient of a scalar function phi is d phi, which is really a set of partial derivative with respect to the space-time coordinates. Partial derivatives with respect to space-time coordinates. d phi over dx mu, theta mu. Now, if you're making a transformation, right? So we simply use the chain rule. We use the chain rule to describe transformation, right? So d phi over dx mu prime is dx mu over dx mu prime, d phi over dx mu. So what is that? We're seeing how the old coordinate changed relative to the new coordinate. So this is given by the inverse Lorentz transformation. So this is lambda mu prime mu d phi over dx mu. So what is a gradient?
How something changes with respect to space.
Yeah, but what type of object is it?
An operator?
No. It's a covector, right? You're used to think of gradients as vectors, but no, they actually belong to the tangent space. You don't see that in Euclidean spaces, but they actually are. So a gradient, because of that, right? Because of the transformation law, is the inverse Lorentz transformation. A gradient is a covector. Now, because of that, there is a short notation which I'm going to use quite often. So instead of writing d phi over dx mu, I'm going to use either d mu phi, which means exactly the same thing, or even phi comma mu. Means the same thing. Now, being a dual vector, we can operate it on a vector, right? So we can operate a gradient on a vector. V is V mu E mu. So if I write down V mu is dx mu over d lambda, then what I get is a simple ordinary derivative. So d mu phi dx mu over d lambda. I can simply use again it's not even the chain rule, right? I just get d phi over d lambda, right? This is just the derivation of the function phi along the curve lambda. Okay. I think I'm confused enough. Just one thing, right? Okay, I'm going to put the problem set today, so you can start thinking of the things. There will be one question which I haven't given you, right? I've defined vectors. What did we do now, right? We've defined vectors, right? After we introduced last week Lorentz transformation and the 4-coordinate vector of coordinate, I generalized that today. I introduced a vector as any object whose components transform the same as the coordinate system. And then I said, hey, the components transform. The vector doesn't care. So what happens when I'm changing the basis? Then I saw that the set of basis vectors, they change not the same way. They cannot transform the same way. They transform the opposite Lorentz transformation, the inverse Lorentz transformation, which is also a Lorentz transformation. So they cannot belong to the same space as the tangent space. They must belong to a different space, which is the cotangent space. And then I generalize that and say, okay, actually this cotangent space contains many objects, which I call covectors, and I denote them with a lower index. Right? And when they operate on vectors, then I get numbers. The same way as we have for row vectors and column vectors. Slightly more general because then I define that also vectors can operate on covectors. Now it's the same mathematical structure as you have seen in your linear algebra course. And also in the quantum mechanical course, that you might not have saw it like that when you were told. But this is what it is, right? Bras and cats represent objects that don't live in the same space. Like you cannot add them together. You can operate them one another, but you cannot add them together and you cannot subtract them. Okay? Why do we need that? I said I'm looking at covectors as linear maps of vectors that takes a vector and gets to R. Now I can generalize that. They take one vector and give me a number. But I can think of objects that take more than one vectors and give me numbers. They're also linear maps, but they're multilinear maps. How do I call these objects? Tensors. This is what tensors really are, multilinear maps. All right. Any questions before we go home?
Yes. There's a little. It's on topic but off topic, mostly because it's ahead. I'm trying to connect this with what I know, and I want to ask if we can define gravity as a gradient, as we've written here on example 3, because
I don't know what is here. I don't know what you're looking at. You mean the gradient? Are you asking whether gravity is a gradient?
Yeah.
No, gravity is not a gradient.
Okay.
Gravity, I said that in the first lecture. That's the real ingenuity of Einstein. Gravity is the curvature of space and time. It's the fact that space and time is not Euclidean. So the correct thing to think of it, and we'll talk about that down the line, right? The correct way to think of it, you know this example of, think of a trampoline, right? Or something which is made out of rubber, and then you put some weight at the center, and then now it's not flat, but it's now somewhat curved. And so if now something is moving, then it will not move, it will move in straight line, but it will look to us like it's being tilted because now the space is curved. This is what gravity really is. But we'll get to that. You're really way ahead of time. Right now, I'm just introducing the basis ingredients to work with. So right now, what I want you, what you need to do is just understand these concepts, these mathematical concepts. And we're still not there. We're still talking about special relativity, so there is no curvature. We're still talking about Minkowski and space. We'll see what happens when we start curving the spaces. We're not there yet. One step at a time. But as you see, remember I told you that immediately you have to follow very closely what I'm saying, because otherwise it's going to be very, very easy to get lost. If I'm going too fast, tell me that. I don't mind adding up an extra lecture just to make sure that I'm going slow enough. I don't think any of you complain that I'm going too slow. If you do, please, no problem. We can make it faster.
Asaf,
Yeah.
the covector and the convector are like the left and right vectors of a matrix.
No, I don't think of them like that. I think of them as objects which live in different worlds.
Okay.
I don't talk about matrices, right? Matrix is a representation of something, right? We had so far two matrices we introduced. One is called eta, and one was called lambda, right? One represented the transformation, Lorentz transformation. One represented something else, which is known as the metric. We will talk about that. So no, I'm talking about objects. For me, I'm looking at them as abstract objects. Vector is some abstract object, which the only thing I can tell about it that is how its components transform when I'm making a Lorentz transformation from one coordinate system to another.
Okay.
Okay, and covectors. So I have vectors. I introduced to you vectors. I introduced covectors. I introduced Lorentz transformation, and I introduced this matrix eta, which we're going to thoroughly discuss, but not now. We're going to introduce, of course, many other objects, but as I said, one step at a time. Okay, but don't go to sleep, because if you go to sleep, you wake up and you see that you've got no idea what I'm talking about. So far, just make sure that so far everything is clear. Right
Where
now,
can we look for some exercises to
I told you.
understand a little better?
Well, I told you. First, I'm going to give you the first problem set today, so you can start practicing. And I told you there is a whole textbook by
Right.
Leitman, Press and Schachter called Problems and Solutions. It's like, I have it on my office. It is in the library. It's an old textbook, but it doesn't matter. These things haven't changed for 100 years, more than 100 years, right? Actually, it was yesterday. Yesterday was the exact day that March 20, 1916 was the day that Einstein published the paper on the general theory of relativity. So go to this textbook, and it's a bit old, but it doesn't matter. And you'll see the first chapter there is about special relativity, so you can simply start practicing solving problems. All right?
So to look for the first chapter in this book.
You normally better start with the first chapter. Okay, it may not look to you like that, but we are starting from the beginning. Okay.
Mhm.
It's not really, it's okay. You just have to get used to the language. That's all. Okay. The last thing I already mentioned, I'm searching for time to add up lectures. So I always prefer to add up extra lectures than to go fast. And I cannot really, and I think you start to understand why, I cannot really stop in the middle and tell you, okay, so we'll just learn 2/3 of the material. No. We have to go through the end, because only then we're closing the loop, and then you'll see the full structure of what happens here. But in the meantime, you need to practice. So I already announced that there will be an extra lecture next Sunday, so 1 week from today. I also don't want to give too many lectures every day, because then it's meaningless. You have to digest what I'm saying. All right. Have a good and quiet rest of the day. I'll see you all on Thursday. And if you have any question or anything, just drop me a mail. And I don't know when I'm coming to office or very present, but we can come and meet there. All right.
Thank you.
Rest of the day.
Thank you.
Thank you.
On Thursday.